धरती पे चाहे जहाँ भी रहेगी, तुझे तेरी खुशबू से पहचान।
Hello, sir. You have joined, sir, now. Yes, sir. Yes, sir. I'll talk here, sir, now. Sir. 1 second, sir. You unmute your this thing, sir. Unmuted, no, sir.
Okay, yeah, no, okay. Now is it okay?
Your sound is coming on now. I am keeping this headphone, sir.
Photo I know.
1 second, sir.
Yeah, Ravi,
Yes, sir. Now sound is coming, sir. We can disconnect the phone, sir.
you can hear me?
I can hear, sir. You can you disconnect the phone, sir?
Is it clear?
Clear, sir.
Okay, I'll connect now to present.
Once, yes, sir. You disconnect the phone, sir. I am able to hear you.
Okay.
Go to the present now, sir.
Yes,
Yes, sir.
present. Taପରେ?
Yes, sir. सर क्या सर?
Present now your
अच्छा यूट्यूब लाइक मैं सर को बोलूंगा 2 बजे स्टार्ट करते हैं फिर.
ताପରେ your entire
स्टार्ट हो चुका है तो फिर तो अभी से स्टार्ट करा दूं सेशन.
share.
ठीक है, चलो कोई इशू नहीं. ठीक है सर. ठीक है, ठीक है, ठीक है सर. ठीक है, ठीक है सर. ठीक है सर. Sir, now we have connected on YouTube live, sir. So you can start the session by 1:55, sir.
तो शेयर ये बंद करिए. देखिए यू आर प्रेजेंटिंग. इसको क्लोज कर दिया.
Cooldown.
मिनिमाइज.
Sir, first you click on this.
Hello, Ravi.
Yes, sir. Yes, sir.
यार ये कहीं कैमरा को
Sorry, sir. Increase your volume, sir. You use headphones, sir. It will be better.
हाँ तो वो क्या केमिकल दिखा दे. देखिए इसके
Sir, you use headphones, sir.
वो हेडफोन यूज कर.
Sound will be better in headphones, sir. Sir, you do one thing, sir. You open PPT in one side. In one tab, you open your PPT, sir.
One minute, Ravi.
Yes, sir.
Hello. Hello.
Yes, sir.
Could you
Sound is little less, sir.
Okay,
Volume, sir.
I'll increase it.
Yes, sir.
Is it okay now? Hello? Hello?
One second, sir.
Okay.
I am joining from my this thing, sir, mobile.
Acha. Sir?
Hello?
Yeah, Ravi.
Yes, coming, sir. Yes, sir.
Is it clear?
Yes, PPT I can see, sir, now.
PPT is visible, no?
Can you keep your mic little bit closer to you, sir?
Sorry?
Mic you can keep little bit closer to your mouth, sir. Sound is little less, sir.
Sound is less. Yeah. Is it okay now?
Okay, sir.
Hmm. Okay. So you're mute, unmute.
गूगल ओपन करो
Hmm.
ओपन करो से ओपन करो देखो ओपन करो ते में देखा जाए हे म्यूट माय कैमरा
Yes, sir.
So, okay. So we'll continue. The voice is clear. Hello?
Hello, sir. Sir,
Is the voice clear?
voice having. I'm listening, but sir, voice is having some issue, I think. Are you able to hear my voice, sir?
Yes, I could clearly hear.
But your voice is coming little this thing, sir. Yes.
Maybe I'll speak little louder. Is it
Okay.
okay?
It's was better, sir. It was better, little better.
Okay. So if I'm at low volume or it has to be increased, you just inform me.
Yes. You make your mobile laptop volume very full, sir. Maximum. Make it maximum.
Oh, laptop. Okay, I'll put it.
presentation
Volume. Speaker.
Let me check how other people are listening.
Yeah. I have put to the maximum.
Sir, on your screen, can you turn on your this thing, captions on? Turn on caption, so that if somebody is not able to understand, they can read.
Which one?
Turn on caption, sir. On your screen, where arrow is there, right to this one. Turn on caption, sir. On your screen, where arrow is there, right.
Caption. Cap lock. What is it?
Yes, sir. Turn on caption, sir. Yes.
captions
Cap lock. Okay.
Turn on caption, sir.
Yeah, I have turned on.
Now done, sir. Make it full screen, sir.
Okay.
Done, sir. Make it full screen, sir.
Hmm.
Now done, sir. Full screen, sir. Done, sir. Make it full screen.
Is it okay?
Yes, sir. Nice, sir.
Okay. The volume is okay, or I'll reduce.
Volume is okay, sir. But Little bit less only. No issue, sir.
Okay, maybe I'll come to the nearer to the laptop and speak.
In couple of minutes, we'll start, sir.
Okay, fine. ये कर दो जी, आप कर दो जी ना वीडियो.
ठीक है, आप इंट्रोड्यूस अगर करा दो, फिर स्टार्ट करता हूँ ऑडियंस को. मैं हाँ मेरा मतलब sir, make it PPT on the full screen, sir. Make it the full.
Yeah, I'll do that.
ठीक है, sir, start introducing.
So, a very good afternoon to all of you. This is Dr. O.P. Verma from Department of ICU, NIT Jalandhar. So, I welcome you all once again in the second day of the second session. So, I welcome Professor Upendra Behra from ISC Bangalore, Center of Cryogenic Technology. So, I am handing over the session to Dr. Ravi Verma so that he can introduce our expert. Thank you very much. Stay tuned.
वीडियो कहीं हाँ.
So, good afternoon, every participant. Good afternoon, sir. So today we have Professor Upendra Behra from Institute of Science, Bangalore. Sir is going to cover two topics in this short-term course. One will be storage and transfer of cryogenics fluid, in which sir will be covering need for storage and transfer system, design aspects for storage and transfer system, insulation in cryogenic system, research finding on cryogenics transfer line. And he will be available tomorrow afternoon session also one more time. There he will be covering about vertex tube technology and its application. There they will be covering what is the introduction to the vertex tube, principle of the operation of the vertex tube, and the different application of the vertex tube. So before we join the session, I would like to thank sincerely to my guide, my guide, Dr. Upendra Behra sir, who is the principal scientist in the Center for the Cryogenics Technology at Indian Institute of Science, Bangalore. If I talk about sir's academic qualification, sir has obtained Bachelor in Engineering in the Department of Mechanical Engineering from Utkal University, Bhubaneswar. Later on, he joined IIT Kharagpur for the MTech, and where he did get MTech degree in the field of cryogenics engineering, and he has obtained his PhD degree from ISC Bangalore. So, sir has been member of some professional bodies. Few of them are Institutes of Engineering India, Indian Cryogenics Council, Instrument Society of India, Cryogenic Society of America, American Institute of Aeronautics and Astronauts. So, sir is the life member of the last 4 professional bodies, and sir is a fellow of the first one, that is Institution of Engineers India. Such research interests are studies on thermoconductivity of materials down to 4.5 Kelvin, design and development of rigid and flexible cryogenics transfer line, vortex tube, air separator, cryo cooler, cryo grinding, and cryogenic system. Sir has more than 80 international and national publications across and conference paper. Sir has got best paper award couple of times, and he also has 2 patents. So without wasting much of the time, I would like to invite Dr. Rupendra Behra sir that please come and give a talk, sir.
Okay.
Sir, you can start, sir. Thank you, sir. Sir, please make the screen full, sir. That's it.
Okay.
Thank you, sir.
बंद कर दिया
Eta.
ना से मिनिमाइज PPT on slideshow.
Yes, sir. Now it's okay, sir. Best, sir. Thank you,
It
sir.
is okay from our side, sir. And your side also. You can proceed further, sir. Thank you.
Yeah. So thank you very much, Dr. Ravi, for introducing me for this this course, short-term course on cryogenics and composites. First of all, I would like to thank all the organizing committee of this STC on cryogenics and composites, theory and application, organized by the Instrumentation and Control Engineering Department of NIT Jalandhar. I would also like to thank Professor Singla, the HOD of Instrumentation and Control Engineering Department, and Dr. Professor Aswati for arranging this event. I am privileged to deliver this talk, storage and transfer of cryogenic fluids in this STC today, and I'm very much thankful to Dr. Ravi Verma in the sense that he was my student, and I'm happy to know that he is doing a lot of good things at NIT Jalandhar, and I wish him all the best for his future endeavors. And anyway, it's a great privilege to deliver this talk, and now I'll start this talk on storage and transfer of cryogenic fluids. Okay, yesterday and today morning, my colleague Professor Kasturi Rangan has delivered lecture on cryogenics fundamentals and applications yesterday, and today the materials for cryogenic applications. And I'm sure you are gained a lot of knowledge on cryogenics. But for the people who missed the introductory session, let me talk a little about the introduction to cryogenics and the properties of these cryogenic fluids in brief, because this is essential for go ahead or proceed the lecture on storage and transfer of cryogenic fluids. So to start with, this is my plan of presentation. Brief introduction to cryogenics. As I told, you are all now aware about this cryogenics, what is it, and some properties of cryogenic fluids. I'll be specific for a few properties of these cryogenic fluids, why it is needed for special storage and transport systems, and then I'll speak on design of these storage and transport systems, then insulation in cryogenic systems, and we have developed some transfer lines here at IISc for the requirement of some national interest, and also I'll present the studies on these transfer lines. Okay, as I have already told, so I'll just give little introduction about cryogenics. This cryogenics is derived from two Greek words, that is cryos means ice cold and genes means generation or production. So cryogenics literally means the production and utilization, and when we are producing and utilizing, of course you have to maintain it. So cryogenic engineering deals with production, utilization, and maintenance of low temperatures. But there is a dividing line, because by refrigeration one can achieve some lower temperature, but by conventional refrigeration process it is possible to go up to minus 50 degrees centigrade or so, or one can go up to minus 80 degrees centigrade with solid carbon dioxide. But there is a dividing line, and to go below this temperature or below 80 degrees centigrade, you need special techniques. As Professor Kasturirangan has explained yesterday, there are three fundamental cooling process which one has to use, either induced evaporation or isothermal process or adiabatic process. So to go or produce lower and lower temperature, one has to go to the era of cryogenics. And as I told, by refrigeration, one cannot achieve below minus 180 degrees centigrade, below minus 80 degrees centigrade. So to divide this refrigeration and the cryogenics, there is a dividing line as per the National Bureau of Standards, which is located at Colorado, and they have given this dividing line that the temperature below minus 150 degrees centigrade. This is an interesting number and easy to remember that it is 1, 2, 3 Kelvin. So the cryogenic starts with below minus 123 Kelvin, and we, the cryogenists, generally deal with the Kelvin scale rather than the Celsius scale. So the cryogenics era starts below minus 150 degrees centigrade, and below this temperature, so many wonderful things happen, and you can liquefy all this nitrogen, all these permanent gases, which we cannot do by refrigeration process. So all these gases, permanent gases like nitrogen, oxygen, argon, hydrogen, and helium can be liquefied below this temperature. And also so many interesting things happen in this realm of temperatures. As you have seen yesterday, rubber becomes as brittle as glass in one of the demo experiment by Professor Kasturirangan. Also, you have seen that how metals and alloys change their properties to either reduce the resistivity, or some alloys which can, like he was showing you one uh, magnetic levitation, where he was using high TC superconductors like ytterbium, barium, copper oxide, and it becomes superconductor below liquid nitrogen temperature, because this critical temperature of this superconductor was above 77 K. It is in the range of around 110 K. So you could have seen, and all these superconductors are dimagnets, and it has shown you this principle of magnetic levitation. Then, if you see the living cells pass a state of suspended animation, that means as long as you are keeping all these cell lines, either blood or plant cell or animal cells, as long as you are cooled it properly and putting in the storage vessel of liquid nitrogen, which is very easy to use because it's abundantly available, and also it is inert. That is the great advantage of this uh, liquid nitrogen. And as long as you are putting in these special containers, then it can be stored as long as you want, and when you want to use, you can just remove, and it is the same cell which was earlier. So these are all brief introduction about how the property changes with material, and these are the significant areas. And now I'll go to the properties of some common cryogenic fluids. These common cryogenic fluids, I'm specific here because here, what are the general cryogenic fluids used by people? That is oxygen, argon, nitrogen, neon, hydrogen, and helium. And we'll start with this decreasing boiling point of these gases. We'll start with oxygen, and I'll give you the idea about their boiling point, latent heat of vaporization, and the density. So oxygen, which is 21% by volume available in the atmosphere, its boiling point is 90.2 Kelvin. And if you convert it to centigrade scale, it is around minus 183 degrees centigrade, latent heat of 213 kilojoule per kg, and density of 1141 kg per meter cube. Argon, it is also available in atmosphere of the order of 0.934% by volume, and the boiling point is 87.3 Kelvin. Latent heat of vaporization again around 162 kg per kilojoule per kg, then density 1394. Then nitrogen, which is plentifully available in the atmosphere, 78% by volume. The boiling point at 1 atmospheric pressure, I have already mentioned this, or written in this slide, that it is 77.3 K, or almost minus 196 degrees Celsius. And the latent heat of vaporization is 199.3. Density of 807 kg per cubic meter. Then neon, it is boiling point is 27.1 Kelvin, and it's not plenty available. These are all available in parts per million in the atmosphere, and latent heat is 85.9 kilojoule per kg with a density of 1206 kg per meter cube. Hydrogen, again 20.3 Kelvin is the boiling point, then latent heat 443 and density of 71 kg per meter cube. Helium, it is 4.2 Kelvin and latent heat of vaporization is 20.9 and density of 125 kg per meter cube. If you see the latent heat of water, it is around 2255 kilojoule per kg, and the density, if you compare, hydrogen is the lightest among all the cryogenic fluids mentioned here. It is almost 1/14 of compared to water, and helium is 1/8 of water, the density of water. So this latent heat of vaporization being very less and the boiling point is very less, you need that the latent heat of vaporization of these cryogenic fluids are very less. And I'll give a idea that what is the amount of with the same amount of heat input, 1 liter of liquid argon vaporizes 10 times faster than water, and liquid nitrogen 14 times faster than water, and liquid helium, you can imagine, 100 times faster than water. And the expansion ratio of these cryogenic fluids are very high at 300 Kelvin and 1 atmosphere pressure. If 1 liter of oxygen you want to make it gaseous, then it becomes 797 cubic meter. Okay, 707 liters. Sorry, that is the 700.79 cubic meter. Like that, argon, when expands from 1 liter, 1 liter of liquid to gaseous, it is converted to around 779 liters of gas. Nitrogen, 646 liters from 1 liter of nitrogen. Neon is 1341 liters. Hydrogen is 788 liters, and helium is 701. So if you see for helium and nitrogen, the liquid to volume expansion is almost 700 times, whereas for argon, hydrogen, and oxygen, it is around 800 times. That means 1 liter of liquid, as a thumb rule, 1 liter of liquid cryogen can expand to 700 liters of gas when warmed to ambient temperature. That means such behaviors of these cryogens are of great concern, as rapid evaporation and large expansion may lead to rapid pressurization of the pressure building in the container, and must be taken into consideration while designing the cryo systems, and the safety measures is a must for all these fluids. So as you have seen in a previous slide, that these cryogenic fluids have low boiling point, and also with little heat input, it becomes volume increases very high and it boils up. So to keep it, once we are liquefying it, we have to keep it in special containers for storage, and also special transfer lines need to be used to transfer these cryogens from the storage container to the end application. So this is considered one of the critical parts of designing any cryogenic system. And now you need, I told why you need this storage and transfer systems, and there are, now we'll go to these storage vessels. Depending on the capacity, this can be classified into different categories, and based on the capacity, there are viewers are the small capacity vessels starting from 1 to few tens of liters. I can see this is one of the container from Inox India Limited, Vadodara, and it's a TA 55 means it can contain 55 liters of liquid. It's a nitrogen container, so this is 55 liters of nitrogen it can store. And some smaller and up, as I told, smaller containers are also there. This is a typical example what I'm giving, and large vessels up to 1 lakh liters capacity are available. And based on the performance, these vessels, cryo vessels, can be categorized into low performance vessels and then high performance vessels. In low performance vessels, cryogens are stored and it boils up in a few hours. And this generally the insulation is used is rigid foam or fibrous insulation. We'll discuss about these insulations in latter part of the presentation in detail. Then high performance vessels where the boil off rate is 1% of the cryogen stored in that container. They are especially, these vessels are with a MLI, that is vacuum plus Mylar insulation. This also will discuss later. This shows typical cross section of one of the cryogenic containers, small dewar, and you can see it consists of one outer vessel, then one inner vessel where these cryogens are stored, and these are some canisters where you can keep some samples and dip it in liquid nitrogen. And you are something we'll discuss the design of these containers in later part, and it has some adsorbents which absorbs any gas evolved, that is the degassing they called evolved inside the container. Inside the container means the interspace between the outer container and the inner container, and these are the insulation part where multilayer insulation, that is vacuum plus Mylars are put, and this is the neck tube specially designed with low thermal conductivity materials like fiberglass, and they call it fiberglass neck tube. And these are suspended, these small dewars generally suspended from the top, from the outer cell or the outer vessel. And these are not closed fully because there is no safety arrangements in this, and these lids are loosely fitted with some with some cork material, so that let's say this thermal conductivity is less, and whatever gas is getting, whatever the cryogen is getting boiled off, that can easily pass on. And sometimes they put slits, they make some passage in this cork so that the gas can easily escape. And this is the locking cover, of course, just to close it. Okay. And in for shapes, there are different type of containers. They are starting from cylindrical, conical, spherical, and combination of all the cylindrical, spherical, or conical. And also cylindrical vessels is generally used for transport vehicles. I will come to that. Let us see the other figures. Here you can see these are containers from Inox India, as I told, and it starts from 1.5, and this is the BA 1.5, and it starts and slowly it converts from BA to TA, that is 35 means 35 liters it can store 55 and like that. And these are all cylindrical containers with some conical head. And these all small dewars are not pressurized containers. That means when you want to remove the liquid or the cryogen from these containers, you have to just lift off and pour to your system, or you can take to the subsystem and pour to the system. And these has to be handled carefully, because as I have already explained earlier, these inside containers are being suspended from the outer shell with the fiberglass, and the connection is done by special epoxy adhesives. And so we have to handle it carefully, otherwise there is a chance that it may break. So all filled containers we have to handle carefully. And this is one, these are all non-pressurized, and there is another cylindrical container from Cryopop USA, and we are also using this in my lab. Some numbers are there. And here you can see these are all pressurized containers. That means part of the liquid, which we'll discuss in later in detail, part of the liquid from the liquid space goes to the outside atmosphere. There is a pressure control valve which can control at what rate you want to pressurize this container. And then this container, this liquid, when it goes to atmosphere, it gets evaporated, and as I told, the volume in expansion takes place up to 700 times. Then that volume of vapor is again put to the oil space. What is oil space will come to the next, it will be discussed in latter part. And then you pressurize the oil space over the liquid, and liquid comes out when you want to take out. This is the liquid in or liquid out, and this is the rupture disc. This is the relief valve, this pressure gauge, and this is a level control, differential level control valve. What I was telling that these there are two types of this pressurized and unpressurized already discussed, and these medium to large containers are generally pressurized containers. And you can see this is a large container for hydrogen, and this is all because large containers are generally pressurized containers. And here what I was telling that all transport containers for cryogenic containers, this is from again Inox Air product. Okay, so here there is a though you can store more quantity in a spherical container with large volume and less surface area compared to cylindrical one, but there is a height restriction in roadways, so it is not possible to make taller spherical containers. And because of that, all these transport containers are cylindrical, and if you see that the end, it is either spherical, hemispherical, or elliptical shapes, and that close. And you can see there is a pressure building here, which we'll discuss in later. And with that, they can pressurize the container and drain out. Now the filling is going on from bigger tank to this transportable transport container. Excuse me. Okay, after getting this information, the type of containers, let us see the how these containers or these cryo vessels are designed. If you go to early 1892, Sir James Dewar has developed this vacuum insulated double-walled vessel, and the credit still goes to his name, and these are all known as Dewar vessel. And I'm sure everybody is using this Dewar vessel or the thermos flask, where they are all double-walled, and inside there is no vacuum, and there is inside there is a vacuum, and one surface is being polished uh, uh, to reduce the radiation heat transfer. And when you evacuate, then all the convection heat transfer is reduced. And again, they also suspend this from the top, so that the conduction heat transfer is minimized. So all the three modes of heat transfer is minimized. And these cryogenic vessels are based on the concept of Dewar vessel, where you can see this is the inside container, or the code known as the product container, and this outside shell, the outer container. And in between there is a vacuum, in between there is insulation that may be of different kind, that may be vacuum, that may be multi-layer, or sometimes it is powder with fibrous materials. And also it has some uh, safety or arrangements for filling and draining the container. This is the place where these cryogens are filled or stored. And then also here the vent, whatever boil up takes place, and also pressurizing the container. You have a diffuser, vapor diffuser, and vent, that is for pressurization of the inner vessel and also escaping the vapor. Also, you have a oil space here on all cryogenic containers, though they mention that the container capacity is, suppose, for example, 55 liters. Still, at 55 liter, it won't be full fill touching to the or filling to the full container. There is always a oil space, and 10% of this total volume is kept for this oil space. And this oil space is used to provide used to reduce the vapor pressure increase due to the heat inlet. When this gets boiled off, if there is no space, then immediately my container will have high pressure. So to reduce that, this is being used. Also, it is used that when you use warm gas for pressurizing, then that time this warm gas is not directly coming to the top surface of the cryogen, and it is distributed. And The warm gas is directed away from the surface. If you can see, the hole is at the top, it is not at the bottom, so it comes indirectly and pressurize the liquid. So this warm gas is directed away from the surface of the cryogenic fluid and reduce the condensation of the pressurization gas. Also, anti-slush baffles are used especially in transport containers where it damps the motion of the fluid. Along with that, as I have told, you have the drain and fill line, and these are the stiffening rings to support the inner and outer vessels. So you have seen the schematic drawing of this vessel, and now let us see. Suppose I want to design this container, then what I have to do, how I have to proceed. That way, let us see first the inner container, which one is storing the cryogenic fluid. So all these cryogenic fluid storage vessels are designed as per the American Society of Mechanical Engineers Boiler and Pressure Vessel Code, that is ASME Section 8. It was done in 1983, but now it is getting modified, and the recent one I think is 2017. They have given the recent updated code. Then, apart from that, also British Standards Institution Standard 1500 or 1515 is used to design this container. So, as per that norm, it is designed. Then the inner vessel has to be designed to withstand the internal pressure in that inside the liquid, the weight of the liquid, and the bending stresses what is arising because of the support. And you have to selectively use the material compatible with cryogenic fluids. And today morning there was a session, and you must have understood that why these materials are only being used for cryogenic applications, and especially stainless steel, aluminum, monel, and copper being used for these containers. Monel is a, this is a mixture of nickel and copper, along with a small percentage of manganese, iron, and carbon. And so, depending on the quality, they change the percentage composition, but the nickel percent vary from 52 to 67%. Okay, so then the inner vessel has to be designed such that it should be as thin as possible, because when you use thick material, your material cost will increase. So it should be low cost by making it as thin as possible, but it should withstand the pressure what is required for us. And so there is special formula which you have to use, which will come in the next slide. And this when this material thickness is less, your this bulk material or the quantity of material, the mass of the material to be cooled down is less, so it takes less time to cool down. So these are the two important parameters, like low cost and less time to cool down. So you have to use the wall thickness as thin as possible, keeping into mind that it has to withstand the pressure, including the weight and the bending stresses, which and also the dynamic load coming on this when it is a transport vehicle. Then the stiffening rings, as I told, it is used for support the weight of these fluids. There's the inner vessel design. This is the equation which is generally being used, and this is as per the ASME code. That is T, that is thickness of this cylindrical cell. Thickness of the cylindrical vessel will be equal to P into D by 2 SA EW minus 1.2 P. That is, P is the design internal pressure, D is the inner diameter of the cell, and SA is the allowable stress, EW is the holding efficiency. And if you do little calculation like D can be replaced with D0 minus 2T, D0 is the outer diameter, then you will land up with this equation P equal to D0 by 2 SA EW plus 0.8 P. And this is only the cylindrical vessel which is being used, but at the end you are having either elliptical, hemispherical cells or the structures. So for that you have to use this second equation, which is TH equal to PDK by 2 SAEW minus 0.2 P, and which again comes to P D0K by 2 SAEW plus 2P multiplied by 2K minus 0.1, where K is a constant, and that is given by 1 by 6 whole multiplied by 2 plus D by D1 square, and D1 is the minor diameter of the elliptical head. Okay, so these two diameters are available. You can find K, and you can get the thickness of both the cylindrical vessel, inner vessel, as well as the head, whatever being used. Similarly, the outer vessel design would be based on the first one. Inside vessel was designed for the internal pressure, whereas the outer shell is now designed for this buckling or collapsing, because now the atmospheric pressure is coming over that, and it generally fails because of collapsing or buckling, and the cylindrical shell will collapse under external pressure at the stress value much lower than the yield strength of the material. And so we have to consider the collapsing or the critical pressure for our long cylinders exposed to external pressure. So this is the equation. The second equation at the bottommost is given for long cylinder, how to define the long cylinder. When L by D0 is greater than 1.140 into 1 by nu square to the power 1 by 4 multiplied by D0 by 2 to the power half. If L by D is greater than this right side value, then that is known as long cylinder, and we have to take this equation for getting the thickness, considering the critical pressure. Pc equal to 2E multiplied by T by D0 cube by 1 minus nu square, where E is the Young's modulus and nu is the Poisson's ratio. This outer vessel, as I have told you, for long cylinders, that is the equation, and for short cylinders, from that equation you can find out whether it is long cylinder or a short cylinder, and from that you can find out. Okay, you can get from this equation you can find the thickness of the for short cylinder, thickness of the short cylinder which is being used for outer vessel, and the hemisphere or the elliptical head you can find out from the below equation, that is Pc equal to 1 E in Young's modulus into Ts, that the thickness of the head by R0, outer diameter, outer radius of the head to the square by 3 multiplied by 1 minus nu square to the power half. And when we are designing all these containers, as per the SME code, factor of safety is taken as 4. So we have now considered for the thickness for this inner cylinder and the outer cylinder with these ends, whether it is elliptical or hemispherical. Now to support this inner vessel to the outer vessel, we should design the suspension system. This suspension system, the support or suspend the inner vessel within the outer vessel, and it should take the load of the vessel along with the weight of the content, that is the liquid inside the cylinder when it is in full capacity, and then the dynamic load. And if the suspension system is not good, then this will nullify the effect of insulation, the container mentos to the outer one, and then your effectiveness of this insulation won't be there, and then a lot of heat transfer will occur, and you cannot able to store all these cryogens. So the commonly used suspension systems are high strength stainless steel tension rods like this, as shown in one, and then the saddle bands of metallic plastic, then plastic compression blocks or stack disc, then compression tube as shown here in 3, and either wire cables or chains, it can be also suspended. And this is one of the picture which shows the suspension system. You can see this is the wall of this inner container, and with a pad it has been connected with a bracket, and this bracket is supported as you can see in the previous slide. This bracket is supported from the top to the bottom, and here an interesting thing you have to remember, that here we are using the plastic or the the low thermal conductivity washers, so that there is no metal to metal contact. This rod and this strap or the bracket is not touching, and so because a insulator or low thermal material, so the heat transfer from the outer container to the inner container will be minimized. And the heat transfer across the support load, this is the equation which is given kma Th minus Tc by L, and this is the main Km is the mean thermal conductivity rod, Ts is the temperature of the warm end, and Tc is the temperature of the cold end, A is the cross-sectional area of the rod, and length L is the length of the support rod. After supporting this inner container to the outer container, then you have to see the piping system, how you have to fill liquid cryogen to this container, inner container, and take out from that. And also again draining system that will come, draining will come later. Now we are considering for the piping system. To fill or remove liquid to or from the inner vessel, you need piping system. Also venting the vapor, you need the piping system. With proper designed piping system, the heat transfer down the piping is due to conduction only. Okay, this the piping should be as long as possible, and it should be of thin wall, and also with insulation. Vacuum insulation is generally being used. There are 3 different configurations which we'll discuss in the next slide, and generally we use schedule 5 or schedule 10 pipe, because these are all thin walled tubes, and these are quite useful or being useful for these cryogenic container designs. And also you have to see some arrangement where the thermal contraction of all these materials or all these pipings, whatever you are using, should be taken care, because you have already seen how the material property changes with temperature, or I think Kasturangan sir must have given some idea. So when, and because all these materials have one linear coefficient of expansion, and when it is cooled, the same thing, linear expansion and contraction both are same, but in different region. So you have to consider that, otherwise there will be stresses in the pipeline, and there is a chance of failure. So there are 4 different type of pipes. This piping system is being used. The arrangements are shown here. The first one is the commonly used multi-layer insulated, commonly used in multi-layer MLI containers, and in that this long length of the pipe is obtained between the warm outer vessel to the cold inner vessel by extending the vacuum space around this, the extended vacuum space to this pipe, so that the heat transfer is minimized. Okay, this is the one of the best arrangement. And the second one is one of the don'ts in cryogenic vessel design, because here this is a poor arrangement, condensation, because it's directly connected to the outer shell, and so this is at room temperature, so direct this condensation of the vapor will take place along the top of the horizontal portion of the line exposed to the fluid, and then this liquid will flow along the horizontal section of the line and to the warm portion, and again it will allow more heat transfer. So heat will get transferred to the inner container by this boiling, condensation, convection process, and no arrangement for thermal contraction in this arrangement. And the third one, if you see here, they have used the thermal, the bellows for thermal contraction, and vertical rises in vacuum space is used, because this can take care of this percolation of the liquid, which we'll see in the next arrangement. And in third arrangement is like that, but they have put the expansion bellow inside this space, that insulation space or the vacuum space, which is this leak may occur because these are all thin walled bellows, and this leak may occur because of fatigue failure, because continuous cooling and heating of the container when we are putting cold, that time also it gets raised, and when it is coming to room temperature and again cooling down to this cryogenic temperature, or the cryogens are being transferred or coming to room temperature and again refilling, that time this fatigue may occur, and that time it is difficult to maintain, and also it is a very costly affair to repair that. So The best piping arrangement in the cryogenic vessel is the expansion bellows, use of expansion bellows in the stand-up area. Stand-up area means here, because this outer shell is generally used by carbon steel, and inside is generally SS304 or so, and it's thin walled. Here you can go for carbon steel and the thickness can be more. But when you are using SS pipe to the inner container, that time when it goes through this container, which is carbon steel, that time this cool down and it may damage this area. So this bellow is, if this part is stainless steel again, then this bellow can be welded, put there, and can be put there. And so the stand-up region bellows, they have put it, and again, as I told, because it's outside the outer container, so it can be easily repaired. And they use this vertical rise to prevent the percolation of liquid within the line. And the same equation for the as per the pressure vessel code, boiler and pressure vessel code, this same thickness and same equation is being used to find the thickness of this pipe. Then along with that, when you are filling the container, you should have provision to take out this liquid, and that is called draining the vessel. And or sometime you have to completely drain out the liquid in the container, and for that draining system is needed. There are three methods generally used to take out this cryogens, whatever stored in the inside vessel, inner vessel. And one is self pressurization, the second one is the external gas pressurization, and the third one is pump transfer. So by self pressurization, as you are seeing a container, this is again from Inox CVA, and this is a 1,000-liter capacity which is being used at our center. This what happens with self pressurization, they removes part of the liquid from the inner vessel, and it goes to the vaporizer or to the evaporator. And here the ambient air or the ambient temperature, when this liquid comes out, it gets evaporated, and again it goes to the LS space, and then it pressurize the container, and then you can able to take out the liquid. By external gas pressurization, you have to pressurize the container, as the name indicates, by external source. Maybe you can use compressed gas cylinders, whatever gas is there. You can use nitrogen, generally being pressurized by nitrogen gas, because helium is a bit costly. It's very costly compared to nitrogen because it's plenty available. And then other method, what they use, remove the portion of the liquid from the inner vessel, then pressurize it with some machine or compressor, then vaporize it by electrically heated vapors. That way it is faster compared to the self pressurization, but it is faster, but additional equipments are needed, like either gas cylinder or the compression system for pressurizing the liquid, which are taking it to vaporize and filling again for pressure building. The third one is the pump transfer. Generally, this is connected to the drain line of the container, and generally used for big storage containers, and where the large flow rates are needed, either for filling the transport containers or where the requirement is more. That time also they use this pump transfer for taking out the liquid at a higher flow rate. Along with these lines, this storage container, inner, outer, and then all your pressure building and draining. Then another important factor is the safety devices. The safety devices generally used toward the inner vessel vent line, and these are all this is, you can see, this is a valve, and this is a pressure, this is a vent valve, this is the pressure safety or relief valve, and this is a bursting disc. This is additional, in addition to this, for redundancy, they have put this bursting disc for the inner cell, so that it should not at any time burst. Okay, so what happens in this is Safety valve is generally spring-loaded safety valve, and this gas pressure cannot exceed the design pressure by 10%. So these are all spring-loaded, and the spring load is adjusted so that when this pressure inside the container is around more than 10% of the design pressure, this safety should open the seating of the valve so that this vapor, high pressure vapor, which is generally set by the relief valve. After that, when it exceeds, it will relieve. And once this pressure comes down below the set value of this valve, then it will sit on that and it will close so that there won't be any vent going out, keeping the container safe. And if the by for some chance the safety valve is not opening, or the unable to vent the quantity of gas inside the vessel for some reason, if the pressure is very high and the more volume flow is needed to be removed or to be escaped from the container, and if it's not able to handle, that time also this rupture disc takes care. And this is again set 10% more than the set value of the relief valve. That means 20% of the design pressure. So when the pressure is more than 20% of the design pressure, and if the relief valve is not able to handle this pressure, that time this bursting disc will open up, and that time this container will be depressurized. But this is a two-way process, means once the relief pressure is relieved, it can automatically close and the container can be utilized, and or later you can remove the liquid. But when the bursting disc is cut open, that time it has no seating. So you have to, actually there is a film of some thick milers depending on the pressure of the inside container, and there is a conical pointed conical dome, which is again supported by some pressure relief pressure relief spring. And if the pressure is more, this disc just puncture to that or it presses to that film, so that the film ruptures, and then the pressure can be, or this pressurized vapor can be removed and the container can be saved. But we have to replace once if at all it is opened, and generally this relief valve works, and this is the double redundancy or a redundancy for the safety valve. Then there is also a annular space burst disc assembly is needed to protect the outer vessel from the external pressure. If at all some external pressure, the external pressure is coming to the internal vessel, then that time here the pressure will increase, and this can this has to open. And also it prevents collapsing of the inner vessel due to excessive external pressure. Okay, and this rupture disc, if the pressure within this interspace is exceeded by 35 kilopascal to 50 kilopascal, then that time this rupture disc opens up or it bursts. So then these containers both are safe. And this happens generally when there is a leak from this storage space to this insulation space. And because when it is entering, the pressure goes dramatically high instantly. And so the rupture disc is here so that it can prevent bursting or failing both the containers. Then there are several type of insulations which are being used for these cryogenic containers. These insulations are also very important because based on the efficiency or the performance of these insulating materials, all these containers perform, or the quantity of heat in leak to the inner container can be minimized. And based on the requirement, one can go for expanded foams. These are the different type of insulations: gas filled powders and fibrous materials, then vacuum insulation, or again this powder insulation what they are using, it can be evacuated so that the performance can be further improved, or opacified powders can be used, which is again better. And the best insulation what I have told, or what generally people use, is the multi-layer insulation, but again it is costly. So all these specific insulations to be used for a particular application is determined through the compromise between the cost, ease of application, weight, ruggedness, etc., in addition to the effectiveness of the insulation. So let us see quickly what are these different type of insulation. Expanded foam insulation have cellular structure formed by evolving gas during the manufacture of the foam. Generally, polyurethane foam, polystyrene foam, rubber, silica, and glass foam are used, and the foaming agent is gas is used as carbon dioxide. This disadvantage with all this type of expanded foam insulation that it has more thermal contraction, and when it is operating at a cryogenic temperature, these foams can crack during cool down, and because of this more shrinkage than the vessel. So again, water vapors and air flows through the crack and reduce the insulation effect. So this for not very effective, but can be used. And then gas filled powder and fibrous insulation, gas filled like the fiber material like fiberglasses, powder cork, perlite, which is called silica powder, then santocell and rock wool and vermiculite. This can be used. And the reduction or elimination of convention due to small sized void within the material. For very fine powders, the distance between the particles may become smaller than the mean path of the gas, so that the gaseous condition, this gaseous conduction shift from continuum to premolecular conduction, and the effective thermal conductivity reduces. But this disadvantage is that moisture and air can again diffuse to the cold surfaces, and this is not useful for hydrogen, helium, or all these applications. Then insulation, vacuum insulation, this extensively used for small laboratory sized divas where they are not putting this MLIs, and this eliminates the solid conduction and gaseous convection, and the heat transfer is also minimized, and mainly because of radiation and the gaseous convection of the residual gas. But when you are removing the gas, these molecules in between the interspace, this also can be reduced. And this radiant heat energy is given by the well-known this equation, Stefan Boltzmann equation, radiation heat transfer. And this is you all aware that AP1 to 2, that is the surface for different surfaces configuration factor for surface 1 to surface 2, and this is again sigma, that's Stefan Boltzmann constant. A1 surface area 1 and T24 minus 214 here. Okay, this radiant heat transfer can be reduced by interposing floating radiation shield. So in vacuum, if you put this floating radiation shield, this radiant energy can come down, and the effectiveness of the insulation is increased. Then apart from this powder and fibrous insulation, if they are the gaseous condition, for gaseous condition is primary mode heat transfer in powder and fibrous materials. So the method to reduce that is to evacuate the gas from the insulation space. And if you can see, this is a graph which is actually given the residual gas pressure in torr against the thermal conductivity of the insulation material, the insulation. So you see that from atmosphere to around 2 pascal or around 15 torr, there is not much changes, little change in thermal conductivity, and from 2 kilopascal to again 7.5 or 1 pascal, that is the range from 7.5 into 10 power minus 2 torr. This linearly proportional, and it comes down with the reduction in residual gases, and below 1 pascal the magnitude of gaseous conduction heat transfer is much smaller than the heat transfer by the radiation, but the solid conduction through the powder and the thermal conductivity remains constant. The main predominant heat transfer is by thermal conduction, that the conduction, and so again it is flattened. So effectively, if you are using the evacuated powder, then you can go up to this 1 pascal, and that is the range. Below 1 pascal, it can perform easily, but it can operate up to liquid nitrogen temperature, because lower than liquid nitrogen temperature, there the radiation heat transfer is minimized and the conduction heat load is more. So that time and the temperature range, if you are going for liquid hydrogen or liquid helium, its conduction heat transfer is more, so there won't be much effectiveness. So generally it is used up to liquid nitrogen temperature, either storing liquid nitrogen, liquid oxygen, argon, or like that. Then this is opacified powder. That with this powder, if you put some opacified, adding some opacified material like copper or aluminum flakes into the evacuated powder, again the thermal conductivity reduces by 5 times. So this opacified powder, when you are putting all these addition materials, then your performance of the insulation improves drastically. But the advantage is that it can be used for large capacity stationary storage vessels like large spheres or cylindrical containers. But the disadvantage is that when this opacifiers, there is a chance that it get packed during vibration, and thermal shots may occur, and the thermal conductivity may increase. So for transport vehicles, these are not suitable, whereas for bigger size, large capacity storage containers, this is very useful. Then the last insulation is the multi-layer insulation, which is generally used in the vacuum space in addition to vacuum, alternating layers of high reflecting materials like aluminum foil, copper foil, aluminized mylar, and low thermal conductive spacers like fiberglass, paper, glass fabric, and nylon net. This can be used, and the because now you are having this either aluminum foil, copper foil, or aluminized mylar. These are all conducting materials. So this gets separated by this fiberglass paper or spacers like fiberglass paper or glass fabric like that. Nylon net also is being used. But without using all these spacers, one can also crinkle or emboss the sheets so that they touch at discrete points, and that time no spacer is required. But it's good that you should have thin spacers and low thermal conductive spacers, so that the effectiveness also is used. And when they use these mylars, these are also punched so that the evacuation will be punched, small holes will be there along with the mylar, so that when you are pumping for evacuation, that time this effectiveness of pumping will increase. And this generally is evacuated to the pressure of 1 millipascal, which is of the order of -4 millibar. And when you are using for cryogenic applications, when this cryogen is stored, then the performance or the vacuum pressure may again increase by order of magnitude. So all modes of heat transfer is minimized in this multi-layer insulation, and this is the best insulation what can be used for cryogenic storage and transport systems. Then all these facts we have told about the storage containers for cryogenic fluids. Now let us see a little or whatever time permits for cryogenic transfer lines. So there are different type of transfer lines to start with. Either it is a rigid transfer line or a flexible transfer line, that is depending on the configuration, and then based on the insulation, whether it is a uninsulated line or a insulated line. So uninsulated line means it is just an open line, and nothing, no insulation is used. It's a bare line, I mean to say. And the insulated lines again we can be with fiberglass, polystyrene foam, polyurethane foam, or sometimes foam and fibrous insulated lines also available. Or you have to go for vacuum or super insulated, which is consist of vacuum and mylar lines. Okay, so this is one picture of a rigid transport line where it is tube in tube, that is a straight tube without any flexibility. This is the outer tube, this is the inner tube, wall thickness including that. And then you have a vacuum space here, and you have the pump out port. You have to of course put the safety, and these are the spacers. So you can see this cross section, cut section view, and as I mentioned, outside they have put the bellow, so that when shrinkage takes place, that time this can uh, uh, this can um, adjust the thermal contraction without stressing the outer line. Okay. And this shows another configuration. These are all flexible, and these are better for maneuverability, though it can take a little more, means the heat transfer is a little more compared to the rigid transfer line, but you have a lot of flexibility, and maneuverability will be very easy for this. And here you can see this is a flexible bellow, stainless steel bellow, and it's, inside also another bellow is there. Interspace is vacuum port, and there we have put super insulation. And this is another one arrangement which will come later as the Bernard joint. You can see one end is the vacuum is extended. This is the inner pipe, and the outer one is the outer pipe, and this vacuum in between the interspace is extended till that, and this part fits to the other part, so that this end almost touches to the gap, almost touches to the other pipe, and this vacuum is extended till here. That means when the joint is there, you are minimizing the heat transfer so that your cryogen is not getting boiled up. And this is one commercial flexible transfer line for liquid helium application. And you can see here also, you can see the vacuum is get extended, which you can see in our next slide. I'll show you that. Then there are, depending on the insulation, there are two different types, either insulated lines or porous insulation, insulated lines or uninsulated lines. Uninsulated lines are most economical for short length and for short time flows, short duration of flow of the cryogen, suitable for liquid air or liquid nitrogen flow. And the formation of frost, once you transfer in a bare tube or bare transfer line, then this atmospheric moisture or carbon dioxide gets settled, whereas carbon gets evaporated, and this carbon dioxide, and then this moisture it makes a frost over the line, and because of that the heat transfer is minimized. For example, when a liquid oxygen line, bare line in uninsulated condition, the heat transfer is 1.8 kilowatt per meter square, and when the frost of 2.5 millimeter is deposited over that during the transfer process, the heat transfer come down to 1 kilowatt per meter square, and it's not suitable for liquid helium or liquid hydrogen, but because this temperature difference is very high, and when it comes at that temperature to atmosphere, then it just simply boils up without reaching to the system where I want to use it. Then porous insulation lines has little improved insulation, and where compared to the uninsulated one, then fiberglass, all these polystyrene or polyurethane foams are used. But they are once this cool down, then this moisture, there is a chance that moisture is all this air gets entered, and then this moistures get condensed there, and then it will be very difficult, or this is for safety hazards for hydrogen and hydrogen use. So for that you need a vapor barrier to avoid the diffusion of moisture into this type of insulation. Then this is the vacuum insulated line, where the inner line and the concentric outer vacuum, the inner line and the concentric outer vacuum jacket is used, and then long distance, and this is used for long distance and a long transfer time, and this multi-layer insulation or vacuum alone can be used. Then the thermal contraction is avoided by using U-bent for the inner pipes or the bellows or the outer side. Okay. So then spacers of low thermal conductivity material to support the inner pipe to the outer pipe, you need low thermal conductivity materials of high strength and low outgassing rate and low specific heat. And the spacer materials are generally plexiglass, fluorocarbon plastic, hylum or bakelite are used, and it should be designed so that the point of contact should be minimized, so that less heat transfer will take place. Though these are all low thermal materials, still the point contact should be as low as possible, and these are the different configurations. Sometimes lower spacers also are used to avoid contact stresses between these two lines. And one of the effective joint for long transfer lines, or if you want to dismantle very frequently, then that time this binode joint, which is a high performance cryogenic joint, as I have explained earlier, this from the first line it goes to the end of this where the vacuum extent is there, and it fit to the other line where the gap between the two is minimized, and so that the male portion telescope within the female portion with a clearance such that no liquid can flow between these two spaces, and the gaseous convection is suppressed. And here the sealing is done at a room temperature with a neoprene can be used, and rather than the cold, located at the warm flange rather than the cold end to avoid the low temperature sealing problems. And V-band clamps are used to put it. These are all quick disconnect couplings. KF different series are there, and those are generally used for all these. And where the applications where the lines have seldom taken apart, these field weight joints are done. This is the vacuum line ending here. One other is ending here to the extension, and they can cut open here for repair everything. And this can be at the field. They can directly also joint it so that if it is not used for dismantling again and again, then this type of joints, vacuum joints, used for vacuum insulated transfer lines. Okay, these are the some fundamental aspects which I have told on transfer lines. And the earlier session was for storage viewers. Now at our lab, we have developed some super insulated transfer lines, and some studies we have done on these transfer lines. And this, as I told, this is the development of a flexible transfer line for some specific need for Institute for Plasma Research at Ahmedabad. Okay, so they need these for their tokamak applications for transferring large quantity of helium for their tokamak application, and it is a flexible one for better maneuverability. And initially they have given some data that either 10 to in the range of 10 to 15 liters per minute of liquid helium should flow through this flexible transfer line, and we have done the calculation based on the design parameters given, and also I'll show you some more. Okay, and here you can see this is a joint, end joint. I'll show in the next slide that this is a disconnecting type. That means when, and these are the same with for vacuum port, and then for this is for pump out port, then for our feed through, another one is there for our feed through, and then this is the NW50 coupling if you need to connect one more. This is the inner bellow, and this is the outer bellow. Then hilum spacer we have used, and this is the inner bellow end connection. This is also same, and this is spare for putting some safety or any other requirement. And this is the actual one which I have developed. We have put with some knot arrangement with neoprene ring for sealing the vacuum, and this can be easily dismantled. You can see this end completely comes out of this outer tube. This is a braided outer bellow, and this once from this end it can be removed and come out completely. We have put the hilum spacers, and also we have used some temperature sensors to measure the cool down and how the line is performing, what is the how and what is the minimum or the optimize the number of spacers. All those studies we have done, and this shows the details of this flexible transfer line. This is of 3 meter long, and here you can see the ID is of 26 mm, 20 mm ID of the first bellow, inner bellow with corrugation, and that OD of that inner bellow is 26.8 mm. The outer one is 51 OD, and this is the this 70 mm OD actually. This is the spacer dimension. Okay, and so this gives the detail of the outer bellow, the inner bellow, and there is a joint actually. This is for that, and this all cap 25 and 50 all is being used, and this is the inner tube vacuum extension for some distance, and this is the inner liquid pipe. And we have designed or we have done the calculation for this the thickness of this inner bellow and outer bellow based on the same equations whatever given by this SMA pressure vessel code section 8, and these are already I have explained. So same equations are being used, and the pressure drop also for single phase and two phase flow we have considered. And here for single phase flow, this is pressure drop over the length, or delta P by delta L for unit length. What is this is given by this equation: F is friction coefficient into mass flow rate by cross sectional area square 1 by 2gc rho into din, where din is the inner tube diameter. And this is the pressure drop for two phase flow. This is the well known Lockhart-Martinelli correlation, and that is given by this delta P by delta L two phase flow equal to phi square into delta P delta L over the length, where this Lockhart-Martinelli parameter is given by x square plus cx plus 1 by x to the power half by x, and x is defined by delta P by delta liquid by delta P by delta L gas. And from that you can find out theoretically the pressure drop in two phase and single phase flow, and the pressure drop in flexible transport line, that is for rigid transport line, and this is for flexible transport line. And this equation we have taken from Witzman, that bellow manual. Okay, so corrugated bellow manual, and that's the by Witzman. Okay, and this is the correlation what is given, and we have used it for calculating both two phase and single phase pressure drop in our flexible transport line. And here are some parameters which are given in this correlation, and for the different constants m and n, and for liquid and gaseous condition where it is given CBCL, all that is available in the textbooks, referred textbooks for design of cryogenic transport lines or vessels. Then the different type of heat loads also we have considered, and this radiation heat transfer is this well-known equation where we have taken this emissivity factor and this coefficient factors. Okay, that is the configuration factor. Then emissivity factor multiplied by sigma A1 T2 Boltzmann T1, where this is sigma, you all know that 56.69 into minus 9 watt per meter square K4. And the radiation heat load again for vacuum and MLI is taken for n number of multilayer insulations. This is the standard equation where we have considered the emissivity of the insulating material, and E is the emissivity of the material, and the ES is the emissivity of the insulating material. Okay, so again pre-molecular conduction, we have taken this equation. This is the standard equation, and QG, that is the heat load on the inner tube due to pre-molecular conduction. QG dot equal to G into P into A1 T2 minus T1, where G is defined by gamma plus 1 by gamma minus 1, G into R by 8 by T2 into the power half into FA, and FA is given with this equation, where FA is the accommodation coefficient factor, P is the vacuum pressure, and mu is the viscosity. R is the universal gas constant, and A is the accommodation coefficient. Then the heat load due to the metallic conduction at the ends where the welding joints is taking place, this is given by the equation Qm equal to 2 pi L over the length over the surface length into theta 2 minus theta 1, where this is the thermal conductivity integral theta, and then ln R2 by R1. So this is the equation we have used for heat load due to metallic conduction. Then the time for achieving steady state condition when you are transferring liquid through this transport line, and that is also given by this equation, the summation of mw, that is the total mass of the mass to be cooled into Cw, mean specific heat, which is given as 0.375 kilojoule per kgK, and then T0 is the room temperature minus the steady state temperature or the liquid temperature. Once steady state is achieved, the liquid is flowing through that, minus V, this total volume of the inner line, into rho SS, that is final liquid density, multiplied by USS, that is the internal energy of saturated liquid, minus enthalpy of that inlet fluid, minus rho G0. Rho G0 here is the density of the gas initially in the line, and multiplied by U0, that is the internal energy at the initial condition, minus the enthalpy at the initial condition, liquid condition, divided by M2G2, that is the mean gas flow rate at the exit, again multiplied by HG2 minus HF1 minus 0.5 Q dot SS, that is Q dot SS, the heat inlet from ambient. And this way you can calculate the time required for reaching the total transfer line to the cryogenic temperature, what is being transferred in this transfer line. And for that, because using these equations and finding the data is really difficult theoretically, so we have developed a MATLAB code in our lab. One research student is working on that for his PhD dissertation, and now he has almost finished his part, and this year he will be submitting his thesis. And this is he has developed for single phase pressure drop, two phase pressure drop, and heat load calculations. And you can see that this is the pressure drop for liquid helium flow. As I have earlier mentioned, it is designed for 15 liters per minute or 20 liters per minute. That is the range they need for the end application. And for single phase flow, we have taken, this is the schedule pipe or different diameters starting from 28 or 27, around 27, then 33, 42, and 48. And you can see that very less pressure drop for helium at this diameter for 48 mm. And with obviously when the liquid flow or the rate of liquid flow is more, it has little increased from 12 to around 21 Pascal per meter of pipe. We have plotted Pascal per meter because we have compared our results with the published data. So we have taken for unit meter length. Okay, and this is the for two phase flow, and this as is expected. This two phase flow is in two phase flow the pressure drop is a little more compared to the single phase flow, and similarly. Anyway, these data will be available or can be given as per the request, and so I don't want to much consider on that. But I want to say that when your vapor fraction is increasing, that time your pressure drop also is increasing. You can see this is the black one is for 0.1 point vapor fraction. Means vapor content, void fraction, and the blue one is for 0.3. That means 30%. Okay, so vapor. So that time, once the void fraction is more or the quantity of vapor in the inlet flow is more, that time your pressure is increasing, and this pressure drop is increasing. This pressure drop again for LN2 flow. Here you can see that they are compared to helium for nitrogen. This pressure drop is a little more, and this is because this has a high again density compared to helium, and again because these corrugations are there in this bellow. It is not a simple tube transport line. This is a flexible corrugated transfer line, so the pressure drop is tremendous. Okay, and this is the heat load what we have calculated for vacuum of 0.1 Pascal for liquid helium flow, and this is for LN2 flow. And here this is the radiation heat transfer, and this is the pre-molecular conduction heat transfer. And when you add together, then over the diameter of the pipe, you can see for 27 mm dia, it's around 0.36 watt per meter. And similarly, here for LN2 flow, it has come to around 4.2 watt per meter, the total heat load. And once the pipe diameter increases, the heat load also increases. So little increases. Okay. And they was telling this is the comparison between the experimental results what we have got with our MATLAB code for pressure drop, then for heat load calculation, all that you can see, and the heat transfer, then the pressure drop, all that calculated here, and the mass required for the line to get filled or to be cold, fill the line. Okay. That is the amount of LN2 required, and this is for two data. What I have told that we have done the calculation for liquid helium as well as for liquid nitrogen, and for meter length of transfer line, and the diameter of the inner tube was now I have compared with the data with the diameter of the inner tube 48.3 millimeter and the outer diameter of 101.6 mm with 10 layers of multi-layer insulation and 10 to the power 5 millibar of pressure. This corresponds to that. So you can see easily from this data that whatever data we have got for helium hydrogen, whatever was available by the published data from HALT and Haas Limited, New Zealand, for LN2 flow for similar type of calculation. This is the experimental result what they have done, and you can see that the total heat load through radiation for helium it is 0.01514, and for nitrogen it is 0.1507, and the total heat load through pre-molecular conduction, that is per watt per meter, and this is 0.4975, and for nitrogen it is 0.3737. And if you add all this heat load together, the radiation heat load and the pre-molecular conduction, this is for nitrogen, for example, if you take, and these two, if you add, it comes around 0.5214, 0.5242, and this value is 0.54. So these two combinedly is 0.5244, and this is 0.52. So this is very nearing, and also the total heat load through conduction we can compare with LN2 flow. This is 7.6 through conduction. This is 7.6 watt per watt total heat load, and this is for their experimental data. It is 7.8. Similarly, the total heat load for nitrogen flow, I'm just leaving helium because you cannot compare. But when the data for nitrogen is matching, obviously this value also to be nearer for helium flow if some data is available, but unfortunately it is not available. Only nitrogen it is available, and we are comparing for nitrogen. So the total heat load in watts per meter length of the transfer line with this ID and OD, this what we got with our MATLAB code is 8.23, we can say, and this is 8.34, very nearing. And this mass required to fill the line in kg, this needs 0.8375. And we have, of course, made some assumptions, and here in practical it is 0.95. So you can say that whatever analysis we have done through our MATLAB code for our design calculations is almost matching to the experimental results. So that way it is good indication for designing our transfer line. Then also we have developed one experimental setup for studies on this flexible transfer line for cool down, and how this mylar or different layer of multi-layer insulations is performing on this transfer line, and then the number of spacers. We have done some experiments, and for that we have developed this. We have made this experimental setup for conducting experiment at our laboratory. And this is the typical cool down curve for this transfer line, which we have made for this 3-meter long and of 20 mm ID and 26 mm OD inner bellow. And you can see that, and these are the sensors A, B, C, D. This is from the end, or I mean from the inlet of the transfer line, where this liquid is getting in. And we have put sensors at a distance of 0.5 meter from the inlet. Then at every 0.5 meter interval, we have put up to 3-meter length. So 5 sensors are put, and you can see that the middle sensor, where the both end heat transfer are less, at the middle it is cooling fast. So the bellow at the center is cooling fast, and it hardly takes some 100 to 200 seconds, 150 to 200 seconds, just to till to the steady state temperature, or you can take little more to reach to that low temperature. Okay. Then we have done studies for transferring some certain quantity of liquid nitrogen for 3 different arrangements. When it was completely bare, it was no vacuum for this flexible transfer line, and the quantity of liquid got evaporated from 9 liter is 40.26. When it was put vacuum level in the range of 1.7 10 to the power minus 3 millibar with 28 spacers. That time it was 27.82 liter, and again with nylon rope as the spacer, this has come down to 17.72 liter. So again we want to optimize that. So now this is the cool down curve for this different multi-layer insulations. We have done by varying the number of layers in the vacuum space, and because this also is an important parameter, that what is the number of multi-layer sheets you have to put so that the radiation heat transfer is effectively minimized. Okay, apart from all other source, because now we are removing, it is at high vacuum, and so your gas conduction is minimized, and whatever is there at the end connection, that is the solid conduction, it will be there. But to reduce the radiation heat transfer, this is the different layer of milers we have done. And you can see that by putting 15 to 20 layers of multi-layer insulation, the cool down time is less, and it can first reach to the liquid temperature with around 200 to 250 seconds. Okay. So I mean to say that we have used, so we have optimized to 20 layers of MLI, and after optimizing to 20 layers of MLI, but here we have taken the data for 20 different layers of, again, there we have optimized for 20 layers, but with that same number of spacers, and by varying the layers as you have done the studies. So by varying the layers from 6, 10, 15, 20, and 26, you can see that the rate of LN2 evaporated comes down with increased MLI, and 20 or 26 can be almost same. But again, we have to optimize the spacer distance, because spacer also touching to from the outer bellow to the inner bellow, which is supporting the inner bellow from the outer bellow. So the number also is important, and the material what we are using is also important. So we have used bakelite for our application, and these are all split type ring spacers with some arrangement that it can be opened to 2 halves and again can be joined, and these are the holes where our feed throughs goes in, and this space should be free enough so that this is the spacer, and in between we are having this line. Okay, inner line. And we have done for, as I told, for different numbers by varying the number of spacers, so that what is the effective or the optimized the spacer distance. So that we have done, and we started with 28 numbers of spacers, and here the heat load is around 3.5 3.7 watt, and when it comes down to 9 from 19, 14 and 11, when it comes down to 19, it is around 0.15 watt. So total heat load to the inner bellow. So we have optimized now to 9 bellows, 9 spacers, and with 20 layers of MLI, and also okay, so 9 number of bakelite spacers and 20 layers MMLI, and by varying that, this LN2 evaporated also changed, and you can see with 9 bakelite and 20 milers. So the amount of LN2 evaporated is least. That means this is the least heat transfer to the inner bellow. So we have optimized to 9 spacers for this 3-meter length. So effectively, it is at around 30 centimeter apart, and that is the optimum for our design. And with 20 layers of MLI, only 2.75 liters of liquid nitrogen get evaporated to cool down the line. And after these studies, we have seen that okay, our design and all our experimental data is okay. All our design parameters is matching with the published data. So let us, after doing this research, then we have to do the actual 5-meter long transfer line, which is needed actually for IPR, Institute for Plasma Research, as I told, for their tokamak application. And this is a 5-meter long flexible transfer line, and these are all SS corrugated line. Internal SS corrugated line is there, and this is a binode connection. What you can see, it is up to 500 meter. The vacuum extent is there. This will be used for their end application, and this is to the this is to the storage door, and this is for their end application. Again, this is full actually super insulation, and this super insulation is extended up to the tip, whereas it will reach to the your system where you are utilizing this liquid helium. So and this is to the container, liquid helium container. So this here again, this NW50 quick disconnect coupling is there, and here this is very less diameter. I can show you this one to the, this is the door side, and this is 21.3 thin walled SS tube, and these tubes are not available in India. We have to import it from USA, and it is really difficult to get small quantities for R&D activities. Many companies denied that, but one company agreed for give some quantity, and we procured that. And all these are thin walled. It's very thin in the, and this bellows for your information is around 0.3 millimeter thickness, and these are around of the order of 0.6, 0.7 mm wall thickness. And we have successfully, and this is the diameter. What I want to tell, this is the inner bellow diameter. Inner bellow inner diameter is 34 mm with 41.5 mm outer dia, and the outer bellow inner ID is 85.38, and the outer one is 100 mm, and with that braided flexible braided hose, it comes around 102 mm, and this is, as I told, 5-meter long. And these are the arrangements, this vacuum port and this U-bend, all that I have taken into consideration. And now we have done the experiment, and this you can see the actual 5-meter long transfer line. You can see this is the outer bellow and this is the braided, because we have not sealed say welded it, because if some problem occurs we can open and repair, but it was working well. We have tested it, it is working well, and now the photograph is taken is not welded, but now we have put some rings and it is welded, and also we have done the experiment for cool down. You can see the actual transfer line here, the vacuum extent, and other end this is for the main dewar, that is again with binode joint. Okay. And this is the cool down and warm up curve for this 5-meter flexible transfer line, and we have put sensors at every 0.5 meter interval, and these are the 3 data which are taken at the inlet, one at the middle, that is 2.5 meter from the end, and the other one is 4.5 meter from the inlet. So you can see that we are at the middle, as the previous one we have done for 3 meter. This is reaching the lowest temperature, and this data, this experiment is done with LN2, because open-ended tubes, it is very difficult, or open-ended transport tubes, it is not possible to do experiment with liquid helium, because helium is very costly and we cannot just vent it to atmosphere. But with special arrangements, it will be tested at IPR with a large quantity of liquid helium, and the quantum of liquid helium needed is also very large. So we'll test it there. But before that, this is the information which we have tested, and check that this bellow is working even for liquid nitrogen flow, and there is no sweating, and we have achieved at -4 millibar, but this improves to 10 per -5 millibar when passing liquid nitrogen, and one can see that by 200 seconds easily, or by 3 to 4 minutes, this total 5-meter long transfer line is getting cooled down. And this is the warm-up curve. Of course, for certain period of time, there won't be any temperature rise in the inner bellow, and so it takes some time, then starts increasing, whereas the sensors which are at the top, means some top surfaces, or from the length, so of the inlet, that goes slightly, means immediately it starts warming up. There may be, because this is the flexible bellow with corrugation, there will be some liquid trapping in this corrugations, and because of that it takes some time, and after that again it starts warming up. And this is the information which I have given regarding the storage and transport line design, and also some development of transport line in our lab. I hope it will be some information and knowledge to all the participants, and I once again thank to the organizer for giving me this opportunity to share the knowledge on cryogenics and storage and transport of for cryogenic fluids. Thank you.
Thank you very much, sir. Am I audible, sir?
Yes, Dr. Ravi, tell me.
Thank you, sir, for your interactive session. You have conveyed the information in the best possible way to the participants. In this talk, the in-depth information about the storage and the transfer of cryogenic fluid is shared with the participants. I, Dr. Ravi Verma, along with the organization team of CCTA 2020, want to say thanks to you for giving your valuable time. Before we answer, there are few doubts that there are some queries from the participant. So I have 6 queries from the participant. So the first query is, which insulation is best for cryogenic storage tanks?
Yeah, as I have already explained, depending on the configuration and taking into the effectiveness, when we are thinking the high effectiveness, then you have to go for multi-layer insulation, but the cost is very high. So we have to compromise between the what type of material you are storing, or the cryogen you are storing, and how complicated is the profile of this container, and then cost, of course. Okay.
So one question there is there, sir, what are the different methods for transferring of the fluid?
Sorry, I did not get you.
What are the different methods for transfer of fluid, sir, cryogenic fluid?
Yeah, the different methods, as I have told that transferring, there are three different methods for transferring this. You can do the self-pressurization. Even for liquid helium, you can little pressurize and then you can take out the liquid. But one should not pressurize much because this boiling point is related to the pressure. So if you pressurize more unnecessarily, you are transferring, means more heat or you are boiling up in turn it will boil up more liquid. So that case you can make little, as you know, you are in lab, and up to 2 to 3 psi or sometimes 5 psi will be better or is required to transfer even some good quantity of liquid helium. And the second one is the external pressurization. As I told, you can use cylinders of same gas. If it is liquid helium, you can utilize liquid helium, and if it is liquid helium transfer, then you can pressurize with helium gas. And if you are transferring bulk quantity, now also cryogenic pumps are available. So with that, you can transfer cryogens, and this is specially used for high flow rate, because these pumps are not so cheap. Because for my vortex tube experiment, I was trying to procure a LOX pump, and it was very costly. It was the small pump of transferring around some 10 cc per second. It was costing around 10 to 15 lakhs.
Okay, sir.
So these are the three methods.
So one query from the participant is, sir, any cooling method or cooling system is provided during transportation of the cryogenic fluid for long distances?
Yeah, there it is possible that you can do this vapor shielding. What it means that when this cryogenic fluid is transferring to the transfer line, through the transfer line, and then some quantity of vapor is get, means immediately you will have large quantity of vapor, and that vapor can be circulated over the inner pipe, so that your heat transfer or the gradient of heat transfer is minimized. But it is not a simple process. That principle is generally being used for containers. They called it vapor sealed containers. That means the boiled off liquid vapor that is in cold condition, and that can be utilized to reduce the heat transfer. But in helium like transfer, it is difficult, and also the process is complicated. I have never seen such type of transfer lines being used anywhere.
Okay. So, sir, one more query is from the participant is there any method to separate oxygen from other gases except cryogenics? I think this may be related to your vertex tube, sir. Maybe your next topic.
No, I did not get the question properly. Can you please repeat again?
Is there any method to separate oxygen from other gases except cooling, like except cryogenics? Maybe he's asking, is there any way to separate the oxygen from the atmosphere other than
Yes,
cooling?
yes. There are different methods. Okay, so one can. There are three different methods, specially. So one is the membrane separation. Okay, so there are some membranes which permeable membranes which will allow only oxygen to pass through it, and that way it can be separated, and it won't allow this nitrogen or argon molecules through that. So that is called as membrane separation. And some process is also there. They called centrifugal separation, or even they called rotating disc oxygen separator. That means in the liquid air, they use some disc and to separate it out. And the third type of separation is the vortex tube air separator, which we will discuss in detail tomorrow. And these are the three basic principles, as I know, to separate oxygen. Also, the pressure swing adsorption. This is the similar process like membrane separation, wherein these oxygens are trapped by charcoal molecular sieves. And that is the basic principle of separating oxygen from air. wherein this is being used for our liquid nitrogen plants, where our main concern is for separating nitrogen from the atmosphere, and in rest whatever oxygen is getting absorbed on the circummolecular sieve or in that bed. There are pressure swing beds, and these are twin beds which operates means in regenerator and generating mode. So that time you can vent this oxygen, but that is another method where you can separate oxygen. Okay.
Thank you, sir. Sir, the last question. I have two questions in the web. So there the participant is asking, what are the different ways of measuring the liquid level and pressure in the storage vessel, helium storage vessel?
Okay. So generally, the first principle is that you put direct a gauge. Okay, so which directly give you the pressure, gauge pressure of the container, and there are also methods which are being used, as I shown my earlier slide, that there is a differential pressure gauge. Okay, sorry, yeah. So first you told the liquid level or the pressure.
Means he is asking how to get the liquid level in the storage
Okay.
vessel
Yeah.
pressure.
Okay.
He is asking, can we use Bourdon tube for the pressure of liquid helium?
No, actually, yeah, level you can measure by differential pressure gauge. What they have done is they connect one from the liquid level, because when there is a liquid level, there will be some pressure. It is like similar to the Bourdon tube, but it is closed. One line is taken from the vapor from the oily space, and the other one taken from the bottom where the liquid is means up to the lowest level of the liquid. It can sense that liquid is there. So depending on this height of the liquid, your differential pressure gauge will show some pressure, and that is being calibrated with the level of the liquid. So by seeing the difference in pressure in the pressure gauge, differential pressure gauge, you will be able to tell what is the quantity of liquid available inside the container.
Thank you very much for your valuable time. Hope that your lecture will help many engineers to pursue their research field. Thank you for your time. Tomorrow
Thank
again,
you.
the same time, sir, to 1:45 p.m. in the afternoon, sir.
Sure,
For the
sure.
work.
Yeah, tomorrow.
Thank, thank you, participants. Okay, sir.
Thank you.
So, dear participants, we will continue tomorrow on the third day of the first session by Dr. Gaurav Manik, by Sushanta Kumar Sahu, CSIR Kerala. Okay, stay tuned. Thank you very much.